Alright guys, let's get into solutions. Alright, now solutions it deals with colligative property. Colligative properties are those properties where there is a physical change but no chemical change. Alright, so one amongst it is vapor pressure. So I would be dealing with all those properties later on, but right now let's get focused into boiling and vapor pressure. Alright. Now suppose I have got two liquids and two beakers. Alright, kept open. Now this is low boiling liquid and this is high boiling liquid. Maybe you can think in terms of ether, and let this be water. So high boiling, ether is quite low boiling and this is quite high boiling. That is 100 degree. Alright, and this comes to below 50 degree. Now whenever you have low boiling, you have more of vapor over here, whereas whenever you have high boiling, you have less of vapor over here. Alright, now if vapor is there, vapor pressure is also there. Vapor pressure is there here as well as here. Alright, now I just gave a value of 0.8 atmosphere here for low boiling. Why? Low boiling evaporates more, so vapor pressure more. So I have given it a random value of 0.8 atmosphere. High boiling, so evaporates less, so less of vapor pressure, so I gave it a value of 0.4 atmosphere. Alright, and we are at sea level, so atmospheric pressure working over the surface is 1 atmosphere. Alright, so it's okay. We understood what is the relationship between high boiling and vapor pressure and low boiling and vapor pressure. High boiling, low vapor pressure, low boiling, high vapor pressure. Now let's start heating it. Alright, so we start heating it. When we start heating it, what happens is vapor keeps on increasing. Now vapor keeps on increasing, so vapor pressure also keeps on increasing above the surface of liquid. What happens at a particular stage, the vapor pressure becomes equal or greater to atmospheric pressure. Then it pushes the atmospheric pressure out and starts coming out. That is what is called as boiling. So boiling is when vapor pressure is equal or greater than atmospheric pressure. We call it as boiling. So what we learned is high boiling, low vapor pressure, low boiling, high vapor pressure, and when vapor pressure is equal or greater than atmospheric pressure, whatever be the liquid starts boiling. Now let's get back, revisit this. Now here already vapor pressure was more and here vapor pressure was less. So obviously in order to get from point A to 1 atmosphere, we would be requiring less of vapor pressure, or rather less of heating, or rather less of temperature. Whereas here, to get from 0.4 atmosphere to 1 atmosphere, we would be requiring more of vapor, so more of heating, so more of temperature. Alright, so that's the reason why this is high boiling and this is low boiling, because already vapor pressure is high. So to get 1 atmosphere, it just requires a little bit of heating to start boiling. Whereas here vapor pressure is low, so it requires more of heating to get to boiling. Alright, so we learned relationship between vapor pressure, low boiling, high boiling, and we also learned what is boiling point. Alright, so boiling point is a point where the vapor pressure is greater or equal to atmospheric pressure. Alright, now let us come to this part. Now what do we see here? We see here elevation in boiling point. Now just think of us preparing tea. So we have put, before the water starts boiling, we have put tea powder. Now since tea powder, it's non-volatile, so when non-volatile solute molecule is added to solvent, then what happens? Then that covers some area. Okay, that covers some area. All right. And that's not contributing to vapor pressure. So non-volatile solutes are not contributing to vapor pressure, owing to which it's hindering generation of vapor pressure over here. So now we would be requiring higher temperature to boil, because this in some part it would be covering the surface area, and then it would be also disturbing the entire fluid to generate vapor. So vapor pressure would be lower. So more heating would be required for getting the boiling point, or for getting the vapor pressure equal or greater than atmospheric pressure. So there would be elevation in boiling point. All right. Okay, we learned that. Now let's get familiar with some of the terms which are normally used, like P10, P1, del P and all. Now del P is lowering of vapor pressure. Now when we added solute to the solvent, what it did, it lowered the vapor pressure. And that vapor pressure, the lowering of vapor pressure, is represented by P1, subscript 1, P1. All right. Then we also have another term over here, P10. P10 is vapor pressure of neat solvent. All right. We know vapor pressure of neat solvent was higher than what vapor pressure is of solution now. All right. So vapor pressure of this has been lowered. Now it has been lowered by how much? If we just take the difference, P10 minus P1, that would be lowering of vapor pressure. All right. Now it has been found out experimentally that del P is equal to P10 x2. P10 is vapor pressure of neat solvent and x2 is a mole fraction. All right, so let's get into a bit of calculation now. Del P is equal to P10 x2, where x2 is mole fraction of solute, and we already saw formula for mole fraction of solute was N2 divided by N1 plus N2, where N2 I had told was reserved for solute. All right. So and N we know is number of moles. All right. And N also we know is weight of material or substance divided by its molecular weight. So this is the entire characterization of this stuff. All right. Now, but we are concerned with dilute solution. Now, whatever solute that we have added is too very less in comparison to solvent. So N1 is too very greater than N2. That is, number of moles of solvent is too very greater than number of moles of solute. So why do we need this in denominator? Because there's hardly anything. All right. So our formula for X2 now gets modified to N2 divided by 1, neglecting N2, it being minuscule. All right. So now our formula gets to del P, that is lowering of vapor pressure, is equal to P10 N2 over N1. So this is lowering of vapor pressure. I am interested in finding relative lowering of vapor pressure. So what do? You either say divide both by P10, that is vapor pressure of neat, or take this down there, whichever way you call it as. So as soon as I take it down, it becomes relative lowering, or there's a lowering of vapor pressure, and when divided by neat vapor pressure, it becomes relative lowering of vapor pressure. So relative lowering of vapor pressure formula gets now to N2 over N1. All right, and N2 is equal to W2 over M2, that is weight of material or substance divided by its molecular mass or molecular weight, and this is weight of solute divided by molecular weight of solute, and this is weight of solvent divided by molecular weight of solvent. So on proper cross multiplication, what we get is W2 M1 divided by W1 M2. So this becomes our formula for relative lowering of vapor pressure. All right, so we earlier saw lowering of vapor pressure here. Then now we are seeing relative lowering of vapor pressure. All right, and further, we have also got to talk about del TB. Now what is del TB? Del TB is elevation in boiling point. Now see, since vapor pressure reduced owing to addition of solute, so obviously we have got to heat the solution more to get vapor pressure equivalent or greater than atmospheric pressure. So if we have got to heat it more, then the temperature also has to rise. So this is del TB is elevation in boiling point. So temperature for boiling also would rise. So there would be an elevation in boiling point. So whenever there is depression in vapor pressure, there is always elevation in boiling point, owing to the reason that I explained right now. All right. So what's the formula for that? That del TB is directly proportional to molality. And when that proportionality sign goes, we get Kb here, which is abelioscopic constant. So, and molality, we know, earlier video, I explained what is molality. Molality is moles of solute divided by mass of solvent in kg. So this is solute and this is solvent. So here it becomes, so the formula gets to Kb 1000 W2 upon M2 W1. I already have mentioned that 2 represents to solute and 1 represents for solvent. Alright, keep in mind that number 2 is for solute, with M2, W2, X2, these are all solutes. Always keep this in mind so that there's least of confusion between the number. Alright, that's about vapor pressure, boiling point, elevation in temperature, lowering of vapor pressure and relative lowering of vapor pressure. Alright.